A comet just flew straight past the sun and then completely disappeared. No telescopes could see it. For days, astronomers had no idea what happened. Did it break apart? Did it survive? And then, it came back. Sunlight slams into the comet's surface, and nothing about it is gentle. In a matter of hours, the temperature rockets from deep space chill to nearly 800 degrees Kelvin. But this heat doesn't seep in far. It only penetrates a thin layer, just a few centimeters deep, before the ice inside starts to boil off. That's all it takes. The outer crust, packed with ancient ices and dust, begins to fizz and crack. Water, carbon dioxide, and other frozen gases flash straight from solid to vapor. Every square meter of sunlit surface hurls out hundreds of kilograms of gas and dust each second. This isn't a slow, graceful melt. It's a violent blow-off, like steam bursting from a kettle left on high. The pressure inside the comet's skin builds fast, straining against the dusty shell. For a brief moment, the entire surface becomes a battlefield between heat and ice, with the sun's energy driving off layers that took millions of years to form. Only the uppermost skin takes the hit. The deeper interior remains cold, shielded for now. But on the surface, the battle leaves scars, fresh cracks, jets of vapor, and a haze of dust that will soon shape the comet's next move. Inside the comet, pressure keeps climbing. When sunlight blasts the crust, trapped gases rush to escape, searching for the tiniest flaw. Even a hairline crack can become a fault line. The crust is not strong, just a loose shell of dust and ice held together by forces weaker than a packed snowball. If the gas pressure below the surface rises past a few thousand pascals, it can pry the layers apart. Sometimes the stress is enough to split the crust wide open, sending jets of vapor and dust spraying into space. These fractures can grow in seconds, exposing fresh ice and triggering more violent outbursts. If the cracks run deep or the pressure gets too high, the nucleus could shatter completely, breaking into fragments or crumbling into a cloud of debris. Most comets that wander this close to the sun do not make it out alive. The odds are stacked against survival. Soho's LASCO camera picked up something wild, a sudden spike in the comet's brightness right as it swung closest to the sun. For a moment, PANSTARRS looked almost 2 magnitudes brighter than anyone predicted. But this was not a sign of the comet exploding or breaking up. The real trick was the angle. As the comet slipped behind the sun from Earth's point of view, sunlight hit its dusty coma almost head-on. That is called extreme forward scattering. When the phase angle gets close to 180 degrees, every dust grain acts like a tiny mirror, blasting sunlight straight toward the camera. The effect can boost brightness by a factor of 6 or more. SOHO scientists ran the numbers. No outburst, no solar storm, just pure geometry. The spike faded as soon as the angle shifted. To know if PANSTARRS actually survived, Earth-based eyes would need to catch it again, out of the sun's glare. On April 27th, telescopes on Earth finally caught the comet slipping out of the sun's glare. For days, nobody knew if PANSTARRS had survived, but there it was, bright, unmistakable, and painted with a distinct green glow. That color is not just for show, it is a chemical fingerprint. Spectrographs picked up sharp emission lines from CN and C2 gases, proof that fresh ices inside the nucleus were still turning to vapor. The first ground-based images spread fast, across observatory feeds, amateur forums, and social media. Each shot showed a tight, symmetric coma, with no sign of fragments or fading. For the scientists and skywatchers who had waited through the blackout, it was a moment of pure relief. The comet had not just survived, it was alive and active, flashing its green signal across the sky. The story had turned from loss to comeback, thanks to the eyes and instruments waiting on the ground. The clincher comes from the numbers. Astronomers charted the comet's brightness night by night, stacking each data point against the predictions. If PANSTARRS had lost its core or broken up, the light curve would have dropped off a cliff, or at least shown a ragged, fading trace. Instead, the post-perihelion curve shot up about 1.5 magnitudes brighter than the standard model for a comet of this size and distance. That kind of jump is not just a lucky break. It means the comet's surface suddenly became more active, exposing fresh ice and releasing more gas and dust than before. Calculations point to a 30% boost in active area, with only a tiny fraction of the nucleus lost to space. The nucleus stayed intact, the coma stayed tight, and the numbers tell a story of survival, not collapse. This is where speculation ends and hard evidence takes over. Spotting PANSTARRS isn't as easy as checking a chart and looking up. Even with its post-solar comeback, the comet's glow has to compete with the brightening sky before dawn. The main hurdle is solar elongation, the angle between the comet and the sun. Right now, it is low, so the comet sits close to the sun's glare, buried in thick twilight. That means only a narrow window each morning just before sunrise when PANSTARRS climbs high enough to peak above the horizon, but has not yet been washed out by daylight. For most locations, aim toward the east-southeast about 30 to 45 minutes before sunrise. Binoculars make all the difference. Even a basic pair will pull the faint green coma out of the background haze. Find a clear, unobstructed view, no buildings or trees, and let your eyes adjust to the dim light. The comet will not wait. In a few days, it will fade back into the sky's glow, leaving only the memory of a survivor's brief return. Right now, a survivor hangs in our sky, fleeting and fragile as ever. These cosmic visitors remind us, not everything that endures leaves an obvious trace. Catch it while you can.